We learn in school how to calculate square roots manually, but we are never told and we never ask why the process works. Well, this video is about to set that right. As an example, let us take the number 20,649,507. That's how many comments I'm expecting on this video from you guys, alright? The process prescribes grouping the digits in twos starting from the decimal point, then taking the number formed by the leftmost group, finding the largest perfect square lesser than that number, using the square root of that perfect square as the highest digit of our square root, subtracting the perfect square from the leftmost group, appending to the difference the next group of two digits to form the next dividend, taking the number accumulated as the square root so far, multiplying that by 2, finding the largest digit from 0 to 9, which when appended to and multiplied with the product gives a number less than the new dividend, using that number as the approximation to the current dividend, appending that digit to our square root, taking the difference as shown, and repeating the process as many times as required using each group of two digits moving rightward until the desired accuracy has been reached, in this case at two decimal places, getting us 4544.17 as our square root. So why does this process work? What is the logic behind the steps? I, for one, never understood why is the highest digit of the square root based upon a perfect square. Why use the accumulated square root of the previous stage as the starting point of the next stage? Why multiply that by 2 and why the x into x appendage? To answer these questions, we must first understand that the process is an iterative one of starting with an efficient estimation of its highest digit and then refining the estimation in stages to the accuracy of digits desired. Estimation of the highest digit is taken from the table of squares of the numbers 1 to 9 multiplied by powers of 10. Matching the even order of magnitude 6 of our number, we take 16 million, the closest perfect square lesser than our number, to take its root 4000 as the first estimate of our square root. This answers our first question about the manual method. Since the first estimate got us to the nearest thousand, the refinements will take us to the lower digits. Let us look first at how many hundreds denoted by x we can pack into our refinement. Algebraic derivation and simplification leads us to the equation 80 plus x into x less than equal to 464. Denoting 80 plus x by the composite symbol 8x, we can write 8x into x less than equal to 464. The solution to this equation gives us x equal to 5 and 4500 as our second approximation. This working reveals the origins of the steps in the manual method we were curious about. The use of the previous root as the starting point for the next stage is seen in the expression for refinement. The multiplication by 2 shows up in the binomial expansion of the square of the refinement. The 5 into 5 is the end result of the mathematical simplification of the expansion. So that is the algebraic explanation of the method. There is also an interesting geometric interpretation. The very name of the operation square root signifies a shape and suggests what the geometric parallel of the problem statement would be, and that is, given the area of a square, find the length of the square's sides. In our case, the problem would be to find out that square, that is the side length of the square, whose area is equal to our number 20,649,507. The approach would be to start with the largest square of area less than our number, but having the same even order of magnitude as our number, and to keep enlarging the square sides in known and convenient quanta, for example, in multiples of lower and lower powers of 10, without overflowing the original square until the desired accuracy is achieved. So where do we start? Once again, we take recourse to our now familiar table of squares of the integers 1 to 9 multiplied by even powers of 10. Our area fits between 16 and 25 million, and therefore the largest square with area smaller than our number would be one with sides 4000 in length. This becomes our first geometric approximation to the solution. The width of the gap between the two squares would be reduced in subsequent stages. Let us tally what we have done geometrically so far with the steps of the manual method. The 16 in the difference and 4 in the quotient are clearly the area of the first approximation and the side length. The difference between our number n and 16 million is the area of the gap between the two squares. We now need to close this gap. To do that, we begin by adding strips of width 100. We find that it takes 5 such strips to bridge the gap without overflowing it, adding 500 to the side length of our starting square of side 4000 and thus making 4500 as our second approximation and giving us a square with area 20,250,000. This new square that we got can be viewed as the addition of the three regions shown in pink and blue to the original square of side 4000. The combined area added by these is interesting to relate to the geometric interpretation of the algebraic formula for the expansion of a plus b whole squared. The added area works out to 4,250,000, which is what the next step of our manual method precisely does. The three mysteries of the process, namely the use of the accumulated square root as the starting point for the next refinement, the multiplication by 2, and the enigmatic 5 by 5 appendage to the product, are all directly evident in the geometric working also. The 2 relates to the fact that the added area has two long rectangles. The 4 to the fact that each of these two long rectangles has its long side of the same length 4000 as that of the last square approximation. And the 5 by 5 to the facts that the shorter sides of the two long rectangles are 500 units and that the new blue corner square that got added is 500 units in both dimensions. The 85 by 5 appears quite directly in the derivation and is equal to the area added at this stage. The difference is the thin sliver of the original square that now remains after two approximations, at the end of which we have a square that has an area 20,250,000 and a side length 4,500. The process would be repeated with strips of width 10, 1, 0.1, etc. So those are my algebraic and geometric insights on the manual method of calculating square roots. This slide summarizes what I have shown earlier on both methods. Do leave comments below. And you know what to do with that like button, don't you?